Hi, welcome to lesson 3.2 on line bond structures. I'm not going to lie to you all. I wish you could see my face right now. This is where I really decided that organic chemistry wasn't for me when we talked about line bond structures in college. And yeah, I think in teaching it, I've gained more of an appreciation for it, but you'll have to be patient as I learn this with you and appreciate this in learning it with you. The way I want to start this lesson, I want to start with a Lewis structure. I'm going to draw the Lewis structure for caffeine. It's really, really big. So I'll tell you, line bond structures look awesome. We will be using them for the rest of the year. It's important that we understand them. But I don't know how I'm going to allow you to make mistakes with this. Not everything has to be perfect, but I want us to try to kind of master this technique. And again, when we get back from Thanksgiving, we'll do a lot of practice on this. Again, like not even done drawing the... This is actually a good indicator of why we use line bond structures. Because it takes so long to draw these. Anyways, this is the Lewis structure for caffeine. It is C8, H10, N4O2. Why did I take so long drawing this? Why am I introducing caffeine? Because it's going to allow us to understand why line bond structures are really important and exactly what they are. So now that we have the Lewis structure for caffeine, let's go ahead and draw the condensed structure. And let's make our lives easier and just do partially condensed. God, my writing is horrible right now. As we're looking at this, we can, again, just take away the lone pairs, take away the bonds to the hydrogens, make sure that we're bonding it to the atom that's bonding and not the hydrogens. C. And we don't need any lone pairs because it's just a condensed version of what we already know how to do. Okay, again, like pretty quick to draw this. Still, how can we make this even faster to draw and almost instantly recognizable? This is where we use what's called line bond structures. And again, they look really cool, but they also have a lot of meaning in the shorthand. So a line bond structure is the most common way to represent an organic molecule or compound, whatever you want to call it. In a line bond structure, each vertex is a carbon. No hydrogens are shown. but carbons must have 4 bonds. So hydrogens are assumed. Number 3. No lone pairs are shown. Formal charges are shown if it is non-zero. All non-carbon atoms are shown. And lastly, shapes are similar to Vesper. And what I'm going to do is I'm actually going to take this and attach it side or right on top of what we're going to do here, because we're going to do the line bond structure for caffeine as well. And it might be easier to have it right on top of. So as I follow the rules, it's going to be drawn in a way that follows everything that we just wrote down. So no carbons are shown, but each vertex represents a carbon. So I'm going to start over here, and I'm going to draw one line to the nitrogen. Okay? So instead of having this carbon, this dot represents the carbon. We can assume that that carbon has 4 bonds, which means if there's only one bond going to nitrogen, the rest have to be hydrogens. As we go, we don't have to draw the C. We can automatically put a double bond to the O, another bond to the N. We can do the same thing up here. Double bond to the O, single bond, and we can stop there for now. We have a double bond in the middle. So these little vertices are carbons, okay? N So this is the line bond structure for caffeine, okay? In red, I'm going to highlight the carbons. We have 1, 2, 3, 4, 5, 6, 7, 8. And if we scroll back up, caffeine is C8. The number of bonds didn't change. Everything is still double bonded where it should be, but it's just a nice condensed way to write this. And I'm going to use pink for my hydrogens because those are not drawn. There is one bond coming from this carbon over here, which means we know that there has to be an unwritten 3 H's here. This carbon has 4 bonds. It's good. This carbon should have 3 H's as well, because there's only one bond. This carbon has 1, 2, 3, 4 bonds. We're all good there. This carbon has 1, 2, 3, 4 bonds. We are all good here. Same with this carbon, also has 4 bonds. When we get up here, we have the same thing where we have 3 unwritten H's. And this carbon only has 1, 2, 3 bonds. It needs to have 4. So there's an undrawn H there. This will get a lot easier. Again, only the yellow is the line bond structure. What I want us to be able to recognize, and again, I know we're gonna forget how to do this in a week, but what I want us to be able to recognize is, can we find the chemical formula if we're given the line bond structure? So, finding, or example of finding the chemical formula, let's see if we can find the chemical formula for, let's just say, dopamine. And I give you this crazy structure of dopamine. Can you count all the carbons in this structure? Well, we have 1, 2, 3, 4, 5, 6, 7, 8 carbons. So we have C8. Now, at each of the carbons, how many bonds do we have? Here we have 1, 2, 3, 4. Looks good. Here we have 1, 2, 3. So probably need a 4th hydrogen here. Same thing up here, 1, 2, 3. We probably need a 4th hydrogen up here. Here we have 1, 2, 3, 4, so we're good here. Here we have 1, 2, 3. So we need to add 1 more here, 1 more here. At this carbon, we need 2 hydrogens to satisfy its octet, and here we need 2. So if we count the number of hydrogens total, we should have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Sorry, I lost count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have H12. I'm not sure if that's 100% correct, but I will double check in just a second. There should not be an H down here. This one has 4 bonds already. 1, 2, 3, 4. So it's H11. And then, of course, we can write down our number of oxygens and our 1 nitrogen. So the chemical formula for dopamine looks something like that. And we can kind of come back to this idea, but I would love for you all to try something like this. where there's an actual formal charge in here, and this is called propionitrile. Here we have 1, 2, 3 carbons, so C3. There should be 1, 2, 3, 1, 2, 3 H's to satisfy the octet. And then, of course, we're left with our N up here. This is the chemical formula. But if we wanted to write this as the condensed formula, then we'd want to do it in order of how this comes. So we should have CH3, CN, CH3. But there's 2 of them, so we can put this together and do CH3, 2, CN. And then put a minus next to it, because there's a negative charge. Anyways, we'll do lots of practice on this. Go ahead and work on the activity and the worksheet. Thanks.